Okay, well, let's dive in and solve some problems. First one I want to do is a relative motion thing, relative velocity thing. We're going to have two jets of material from the center of a radio galaxy fly away in opposite directions. A radio galaxy is one that puts out a lot of electromagnetic radiation in the radio part of the spectrum and may not even be visible in visible light. It could be so far away with so much intervening gas and dust between us and it that'll block visible light that radio radiation is the only way we have of knowing what's coming from it. So they both move at 0.75 C relative to the galaxy. So picture-wise, if imagine that it's a spiral galaxy, perhaps, there's a jet of material that's coming out of the plane of the galaxy probably from about the center of the galaxy. Could be a supermassive black hole that's generating those jets of material. But anyway, they're each going at 0.75 C relative to the galaxy. And we want to determine the speed of one jet relative to the other. So it's just kind of a relative motion thing. And, well, here's our formula. It's going to be x prime is equal to v sub x minus u divided by 1 minus u v sub x over c squared. This is going one direction. We can also go the other direction too. But in fact, we did derive these expressions somehow here. But we can pick one of these jets as being our favored frame of reference, maybe this one. And so we can think of this as being our primed coordinate system. That's P-R-I-M-E-D. That's the jet that's headed down here. And we can let x be positive in this direction, or x and x prime be positive in that direction. So anything that's going in that direction is positive. Okay. Well, u will be the velocity of this primed coordinate system with respect to the galaxy, which is the unprimed coordinate system. I'm just going to call it S, and this one's going to be S prime. So the velocity of S prime with respect to us to S is in the negative direction. So u in this case is going to be minus 0.75 C, negative direction there. And then v sub x is going to be the velocity of this thing with respect to, what did I do here? This is supposed to be v sub x prime, not just x prime. V sub x prime is equal to that. Anyway, v sub x can be the velocity of this jet with respect to the unprimed system. So v sub x is going to equal 0.75 C, like that. And we pretty much have everything needed that we can figure out. We want to know the speed of this jet with respect to this jet. Now, without relativity, you'd think, okay, it's going to be going the sum of these two speeds, or 1.50 C. And that's what the numerator of the expression always gives you. But in this case, let's see what we get. We still have that denominator to deal with. So we'll have 0.75 C minus a negative 0.75 C. And sometimes this is the trickiest part, is dealing with the minus signs that come out of this expression. So, and then 1 minus U is minus 0.75 C. V sub x is plus 0.75 C. And we've got a minus and a minus here and a minus there. So between the two of those, that's where stuff gets taken care of. Let's see, numerator ends up being 1.50 C. On the bottom, all the C's divide out, and I'll have 1 plus 0.75 squared. And we can just do the calculation then. And we don't get 1.50 C for the answer. We get 0.96 times the speed of light. And maybe we could somehow argue to keeping 3 sig figs on this, I guess. Looks like we have 3 on top, and this is exactly 1, so, but it just comes out 960 if you do that. So there's another one of those things. Okay, let's try another problem. Whoops, that's just another one of those. I may put it off for a little while. Here's a recoil problem. An unstable particle at rest breaks into 2 fragments of unequal mass, and the rest mass of the lighter fragment is that much, which is going to be less massive than a proton or neutron. And the heavier fragment, I'm not so crazy about lighter and heavier. I'd rather call them less massive and more massive. But anyway, the heavier fragment is 1.67 times 10 to the minus kilogram. This thing looks like a proton or a neutron. We don't know anything about the charges of them, so we can't say. But if the lighter fragment has a speed of 0.893 C after the breakup, what is the speed of the heavier fragment? Okay, so here's our original particle, whatever it happens to be. And afterwards, we have the mass of the heavier fragment here, and it's headed in this direction, whoops, at some VH. So going like that. And then we've got the lighter fragment, M sub L, and it's headed in this direction at 0.893 C. Now, there's no momentum to start with because we had both particles tied up in this thing, and afterwards there can be no momentum. So the momentum in this direction of the lighter particle has to equal the momentum to the right of the more massive particle. And so we will have to use the relativistic expressions, and then later we'll compare this with the non-relativistic expressions. But I'll have, this is the lighter one, I'll have gamma for the lighter, m, the mass of the lighter, times v for the lighter, is going to equal in magnitude gamma for the heavier one, the mass of the heavier one, times v for the heavier one. So that's what we have. And it would be nice, except that, or it would seem easy to solve, except gamma for the lighter and gamma for the heavier also have the speed of the heavier one tied up in there and the speed of the lighter one. But since we know the speed of the lighter one, we know everything on this side. What we don't know over here is v sub h. So let's see what we can do with that. V sub h times gamma sub h would be v sub h divided by the square root of 1 minus v sub h over c quantity squared. So we need to maybe think about just what we might do with this. We can actually solve for v sub h gamma sub h just by dividing the mass out of this thing. And so v sub h gamma sub h, which is this thing, is going to equal gamma sub L m sub L over m sub h times v sub L. And we can calculate everything here. We know that it's going 0.893 C, that's the v sub L. So gamma sub L is going to be 1 over the square root of 1 minus 0.893 squared, and 2.22. So good enough on that score. Let's see. So gamma sub h, v sub h. Trying to figure out a clever way to do this, and I don't see it yet, but we'll think of something anyway. It's going to equal gamma sub L 2.22, and then the mass of the lighter over the mass of the heavier, 2.50 times 10 to the minus 28th kilograms times v sub L. Let's see. Okay, I guess that kind of makes sense. And we'll get something that's a fraction of the speed of light, actually, out of this. I get about 0.297 C. And so that's what I have. And I'm just going to call this thing alpha. Well, I do a bunch of algebra with this thing because, or wherever it went, that alpha there, 0.297 C, I'm going to call it alpha C instead, is equal to v sub h divided by the square root of 1 minus v sub h over c squared. And if I divide both sides by c, I'll get 0.297 is equal to v sub h over c divided by 1 minus the square root of 1 minus v sub h over c squared, which is actually beta sub h divided by the square root of 1 minus beta sub h squared. Okay, now I've only got a single letter that I have to mess around with. It does have subscripts, but if I multiply this out from underneath and square both sides, I'll get 0.297 squared times 1 minus beta sub h squared is equal to beta sub h squared. And a little bit of work, and I'll have 0.297 squared minus 0.297 squared beta sub h squared is equal to beta sub h squared. Bring this across, and I'll have 0.297 squared is equal to beta sub h squared times 1 plus 0.297 squared, or beta sub h is going to equal the square root of 0.297 squared divided by 1 plus 0.297 squared. Okay, and I think that's about as friendly as I can make this thing. So, but that's just a number now. So the fraction of the speed of light that the thing is going. Okay, and I get that beta sub h ends up being about 0.285. Whoops. Oh, that was an equal sign. Couldn't even read my own writing. Looked like something else. Oops, beta sub h is just 0.285, but v sub h is going to be 0.285c. So that's what we get. And it was a little bit of work, but it all depended on setting the relativistic momenta equal to each other. Now, if we didn't use special relativity, let's see what we would get. We wouldn't have the gammas on here. So we would just say m sub l v sub l is equal to m sub h v sub h. The calculation's a whole lot simpler. V sub h is just going to equal, wait a sec, I can't read my writing here. Those are h's, those are l's. There we go. Okay, so just plug in the numbers here. The mass of the lighter, 2.50 times 10 to the minus 28 kilograms, 1.67 times 10 to the minus 27th kilograms, times 0.893 C. And in a lot of these relativity problems, it's okay to just leave the final velocity that you figure out in terms of the speed of light, since that shows up so much here. Okay, I think I get, if I didn't make a calculation error, 1.34 times the speed of light. And so, or no, can't be greater than that. There's an exponent of a -1 on there that I missed. 0.134 times the speed of light. So that's what we get. And we ended up with a speed about more than twice as great as that using the relativistic stuff. And the main reason for that is that factor of gamma, 2.22 on there. It has, the lighter fragment has much more momentum than you would calculate classically. So that's what happened on there.